Hello, welcome back. This is part 3, electrons. We're just going to do a little bit of a review on electrons, where they are, how they exist around the atom. So the first part is the energy levels. Remember we talked about in the periodic table that the periods all tell you sort of which energy level. And so electrons will fill in energy levels, and the closest energy levels to the electron are going to be the lowest energies, and then moving out, blah, blah, blah. So we'd have, of course, starting 1, energy level number 1 just has the s orbital. Energy level number 2, 3, 4, blah, 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 out from there. So the sublevels are those orbitals within that. Like I said, energy level number 1 is just going to have s, and s is kind of a spherical orbital. So energy level number 1 only has s, and we actually symbolize s with the number 0. So this 0 right here symbolizes S. So let's say we were defining lithium. Lithium has 3 protons, and in energy level number 1, it has 2 electrons, and then it has 1 electron in energy level number 2. So this is 1. So we're going to have let's talk about the first electron in lithium. And we'll go through and sort of do all this. So the first electron in lithium is going to be 1 for energy level number 1. And each single electron has all of its own quantum numbers that describe exactly where that particular electron is. So the second quantum number that we're going to have for lithium is going to be 0, because that first electron is going to be in the orbital, the s orbital. And then we're going to go up from here. So each of these orbitals has subshells, or sometimes just called orbitals. There's so we got sublevels, and then within each one of these sublevels, like SPD, there's a certain amount of orbitals. Well, the orbital s only has 1 orbital, so there's only 1 s orbital, so that only can take 2 electrons ever. So that one is always a 0. In the p, though, you can have 3 of them. So the p will have a 1, a 0, and a -1. So that would be the 3 different p orbitals, and we've showed the 3 different p orbitals in kind of 3D format, sometimes kind of like 3 dumbbells intersecting, or we've called them x, y, and z. The d orbital has 5, so we'd have a 0 in the middle. It'd be 1, 2, -1, -2. So this would be the 5d orbital. So if we're talking about that first electron in lithium, it's in energy level number 1. The orbital is s, or the sublevel is s. The orbital within it is 0, because there's only 1 orbital in there. And then the final one, the final quantum number signifies spin. So in a particular orbital, let's say you have an s orbital, you might have 2 electrons. You have an electron here, and they're whizzing around. Woo, there they go. So these things, though, are both negatively charged, and they should repel each other. But they don't. They seem to exist in the same sort of theoretical 3-dimensional area, right? And the reason that they seem to be able to do that is that they spin opposite directions. So one, we say, is positive 1/2, and the other is negative 1/2. And this is looking at the orbital spin. So there's 4 things to define an electron: its energy level, its sublevel, its orbital, and its spin. So when one spins in opposite direction, it actually produces an effect of an opposite sort of electrical field. So they can actually be in that same general area. So let's say this first electron in lithium, it's in the shell 1, or energy level number 1. It's in sublevel s, and in orbital, the only orbital in s, so in 0. And then 1/2. And so that's its spin. The second one, let's say if we did the second one in lithium, it'd be 1, energy level number 1, sublevel s, 1 orbital, and -1/2. So this is those first 2 electrons in the s orbital. The third electron in lithium would be in shell 2. It's also going to be in sublevel s because we start over again. There's another s orbital for energy level number 2, and there's only one orbital in that s subshell, and then this one we could say is a positive 1/2. And there isn't another electron in lithium. Now, oftentimes it wants to lose this one so that it can just have these 2 and have that completed energy level number 1. But these are the 3 electrons in lithium, and that defines their quantum number. So you have a set of quantum numbers for every single electron in every single atom. Here's a couple more examples of this for you. N, of course, is an energy level. The possible values of that are right here. In energy level number 1, the only possible values of L, which is the sublevels, is 0 because in energy level number 1 you only have s orbitals. In energy level number 2 you have s and p, so you have 0 or 1. See, there's 1 right there. In energy level number 3 you have 0, 1, and 2. So in energy level number 3 you can get up to the d orbitals. In 4 you can get up to the f orbitals. So, so here's our ranges and our total number of orbitals in shell, so I hope that helps. And of course, this is very, very fast, and the idea is that this is review for you. Okay, if you need more review on that, book has a really good explanation of it. But stick with me, and we're going to go through. So as far as figuring out how do I know which electron is going to come next and where is it going to go, the Aufbau principle came up with this guy with the last name Aufbau, and he states that when you're building up the electron configurations of an atom, electrons are placed in orbitals, subshells, and shells in order of increasing energy. So they always start here with 1, and then 2, and then they move up from there. So when you draw it out like this, it makes it really easy. So you can just start off, with 1s. It starts with 1s, and then it would go from there to 2s, you see, and then 3s, and then 4. So you just write this down in a linear up and down, and then behind this you'd start with the second one, and then you would go 2p, 3p, like that. And so if you were to write all these out, you get something like this, and then you could draw arrows, or you could just look at it, and they always fill in this direction, right? So you could actually make one of these own charts for yourself real quickly to figure out exactly how an energy levels are filled by electrons. So it'll go 1s, 2s, 2p, 3s, 3p, 4s, 3d. Now you'll see here that the 4s comes before the 3d, and that's because it is actually going to take less energy to fill this 2 electron 4s than it is this 10 electron 3d. But there's some little differences on that, and we'll talk about those kind of special things here and there as we go. After the Aufbau principle, we have what's called the Pauli exclusion principle. And the Pauli exclusion principle really tells us that within an atom, there's no 2 electrons that can have the same quantum number. So essentially, each electron occupies its own specific space, and they can't overlap each other. So they have to have, if they're going to be in the same orbital, for example, like if they're going to be in a p orbital, I always do that. They're going to be in a p orbital. There's 3 p orbitals, right? You have 0, -1, and 1. Or when we've done it before, we've showed them as like dumbbell kind of thing. So here's 1, and then there's another 3-dimensional area like that. Each one of these will contain 2 electrons, right? And their spin will be 1/2, -1/2. And so all the quantum numbers for 2 electrons in one of these p orbitals will be the same, except for this spin at the end. So Pauli exclusion principle essentially says that every single electron has its own set of quantum numbers. Then we also have another rule, came up with from another guy called Hunds rule. And Hunds rule tells us that electrons would like to have their own orbital. And if they have to share They will. So they'll always occupy an empty one if available. So if you look at this right here, so we have 1, 2, 3, 4, 5, 6, 7. So this would be nitrogen, right? So if you look at this, what's happening is in our 1s we have filled them, put 2 electrons in there, and our 2s put 2 electrons in there. Now we only had 3 electrons left over. The p orbitals all have, or the p subshell all has 3 orbitals. Every single p has 3 different orbitals, giving a total of 6 it can hold. And so it's going to put 1 electron in each orbital, and then as it gains more electrons, it'll fill from there. Like if you look here, we have this one showing us that it's going to fill like this. All right. So that's what Hunds rule says. So they'll always occupy a single orbital if possible and pair up if no empty orbitals are available. All right, so last thing on this is the idea of electron energies. So electron energies are what we call quantized, and so that can be a little bit difficult to understand sometimes, but it's important for you to understand, and it means that electrons only exist at specific energy levels. So they seem to not exist in the space between. So if this is my my atom right here, my nucleus, you know, this is the area of energy level number 1, and this is the area of energy level number 2. So that electron can have enough energy to go here, and if it gets more energy, it'll wait till it gets enough to basically jump to here. And so essentially we would say that it doesn't occupy the space in between ever. And so, I mean, I guess you could say that it sort of appears here and disappears here and so forth. So the idea of quantum jumps, or an electron being quantized, is sort of spelled out in these equations. So this is the equation for the energy of electrons. So the energy of the electron, that's what this En is, equals negative 2.178 times 10 to the negative 18th joules. And so joules is how we measure energy, divided by the energy level squared. And so electrons will jump to higher energy levels. Like I said, they won't like do a progressive motion to get from here to here. And when they drop back, they give off that same amount of energy on the way back in the form of electromagnetic radiation. And so that's what this is showing us, is that particular energy, and this is how you would calculate that particular energy between energy levels. And so this right here is talking about the change in energy and electromagnetic, or the energy change. And so if you're looking at the relationship between the energy that is absorbed and released, and so all the light that we have around us, all the light that we see, is actually a result of an electron sort of being up here and then popping back down here, and then in order to go down, it gives off that amount of energy corresponding to the quantum jump that was needed to go from here to here. And so that's what this is. This is energy change. And so for an atom to do this, you first have to give it energy. We do that by throwing electricity into light bulbs or whatnot, and then these electrons give that energy right back off. And so right here, this is the change in energy is equal to hv, which is Planck's constant times a frequency. So, and that is also equal to Planck's constant times the speed of light divided by the wavelength. And so there's several different ways to calculate that change in energy, and we've done that here and there as we've gone along in first year chemistry. So this is just a review, and the main idea is that energy in electron is quantized, it goes in jumps. There are ways to calculate exactly what that energy is. All right.